Alright, so let's talk about the separation test. If you did poorly on the separation test, I'm going to first talk about chromatography, since that was a big issue for some of us. If you do not need chromatography, then skip ahead until the part where I'm no longer talking about chromatography. Alright, here we go. So this is a chromatogram. Remember that chromatography is a separation technique which separates mixtures. Like all of our separation techniques, it's for separating mixtures, not for separating compounds. What that means basically is anything that we're going to be able to do chromatography on, it's made up of multiple components. Like think of that black ink from the lab. The black ink was really a mixture of other inks, and we could see that the red separated out from the green, separated out from the blue, and that's how we actually made the black ink. How does it separate those mixtures? Well, it separates by polarity. So while filtration separates by size and evaporation separates by boiling point, chromatography separates mixtures by polarity. Remember, the way that this works is capillary action. So we put our chromatography paper in a beaker of water where the water is below the spotting line, right? But what that water does is, as soon as that paper, the bottom of the paper hits the water, well, some of that water, a lot of the water actually, begins to creep up the paper against gravity. It follows the paper up, and as it passes through the ink sample, which we put on our spotting line, it's the spotting line, by the way, right here. As it passes through the spotting line, it takes the ink with it. But remember, that ink is made up of multiple components, and some of those components are strongly attracted to the water. So the water has a very easy time carrying those components up the paper. But some of those components are not very attracted to the water, so the water does not pull them as effectively up the paper. They get sort of left behind. So anything that's going to go high on the paper is really attracted to the water, right? Because it's able to be pulled up quickly or effectively. So that must mean then that in this chromatogram, the blue component was strongly attracted to the water, while the red component was not that strongly attracted. And if something is strongly attracted to water, that means that it is polar. So I'm going to write polar, or highly polar is better, by next to the blue component. The red component, I'm going to say not as polar. Still polar because it was attracted to the water. If it wasn't attracted to the water at all, well, it would have stayed down here at the spotting line, but it went all the way up to about halfway. It traveled up 3 centimeters. So all three components are polar here, but the blue is the most polar. And that was a question on the test if you missed that. Okay, let's see. Let's talk about retention factor and what it is. Retention factor is a way to compare chromatograms to other chromatograms of the same mixture. So let's say that someone did a bunch of chromatography experiments on different pens. And so they know that, hey, if I see a chromatogram that looks like this one that I did last night or last year or whenever, I know I can go back into my records and say, oh, this mixture ends up with RFs of 0.5, 0.6, and 0.7. And if I get similar RFs on this new chromatogram of an unknown substance, well, I can say, hey, that substance matches the chromatogram that I did 3 weeks ago, so those were probably the same substance, the same ink, the same mixture. And that's how chromatography is used in forensics. And that's how it was used in the lab that we did. Remember when we talked about who forged the hall pass? We compared data that we collected against like known chromatograms of pens, right? And we could say, ooh, which one was used to forge this hall pass? So that's how chromatography is used. But the retention factor is like a mathy thing that we have to do in order to actually compare those chromatograms to each other. And the way that we calculate retention factor is we take the distance traveled by the solute, we can call that solute distance, divided by the distance traveled by the solvent, we can call that solvent distance. You're saying what the heck is a solute and what is a solvent? Solute is the thing dissolved in the mixture. So this is a solute. The red is a solute. The green is a solute. The blue is a solute. Anything that's going to separate out of our mixture is a solute. Solvent is the water. Solvent is whatever we're using at the bottom of our beaker to help separate those components out from each other. So I'm going to take the distance traveled by, let's do the green one. Let's take the green solute. I'm going to say my green solute here traveled 4 centimeters because it started at the spotting line and it went up 4 centimeters. And I'm going to divide that by the solvent distance. Up here, this dotted line, that's called the solvent front. Solvent front. And it shows us how far the water goes up the paper. In this case, the water went up the paper 8 centimeters. So my retention factor would be calculated by 4 divided by 8, which I know is 0.5. That's my RF for my green substance there. Every component in my that made up my ink, or that made up my mixture here, has a different retention factor. And what I want to point out here is that 0.5 as a retention factor, that's telling us that the green went up 50% of the way. It went up half of the way that it could have gone. It could have gone all the way up to 8, but it only went up to 4, so it went half the way up that it could have, right? That's what that means. That's why that 0.5 is there. We can see that if I wanted to calculate the retention factor of my red solute, I would calculate that by going 3 centimeters divided by 8 centimeters. And I know that 3/8 is 0.375. So that would be the RF for my red solute. Okay, there we go. That is chromatography. If you need to study more on chromatography, then please review the chromatography slides. That's why I put them up. If you never took those notes, that would be why you missed some of the questions. Take the notes, watch the videos. There's videos in there. It'll help. Please do that. Okay. What else is there in separation techniques? You should know that every separation technique that we studied, so evaporation, filtration, chromatography, distillation, all of these are for separating mixtures, and so they all are examples of physical changes that you can make to substances. There are no chemical changes going on here. No chemical reactions, no chemical changes. Because all we're doing is pulling those components of mixtures apart from each other. So remember that. let's do homogeneous and heterogeneous real quick. Okay, these are the two kinds of mixtures that we studied. A homogeneous mixture. This is a mixture with a very small length scale. Very, very small length scale, which means that if you just look at it, if you look at the mixture, it looks the same throughout. So an example of a homogeneous mixture would be something like, well, the example from class was salt and water. We know that that salt dissolves in the water, and it dissolves so small that it's actually on like a molecular level or an atomic level. So we can't see the salt in the water. Everything looks the same throughout. An example of a heterogeneous mixture. This is something with a larger length scale. If you need a definition for length scale, go look at the notes. I'm not going to say it again. I'm tired. And this kind of mixture looks different throughout. In a heterogeneous mixture, you can see the components. You can see all the different components. Let's say components can be seen. A classic example of a heterogeneous mixture would be like salt and sand. If you look at salt and sand, that's going to have some grains of salt and some grains of sand, and you can see the difference, right? You can definitely see the grains if you look closely. Another example of a heterogeneous mixture would be something like a fruit salad. Okay, if you look at the components, or if you look at your fruit salad, you can see that it's made up of different fruits, and you can tell what the different fruits are. With the homogeneous mixtures, you cannot see the different components. So, like Kool-Aid would be another example. Right, you cannot see the Kool-Aid versus the sugar versus the water. It all just looks like one liquid all dissolved together. Okay, so that's the difference between homogeneous and heterogeneous mixtures. A pure substance is neither a heterogeneous or a homogeneous mixture. This would be something like, like water, right? Water is not a mixture, it's just water. We wouldn't say that it's a mixture of hydrogen and oxygen. I mean, water is H2O, but that's not a mixture of hydrogen and oxygen. That's a compound, right? A chemical reaction occurred to put those atoms of hydrogen bonded to the atoms of oxygen. If I wanted to separate my compound here into something other than water, I would need to do a chemical reaction on it. And that's not a part of this unit, right? We just have physical changes here, no chemical reactions at all. So water would be a pure substance. Butane would be a pure substance. Ethanol would be a pure substance because it's stuff that is not in our it's stuff that doesn't have components of a mixture. It's just one thing. Okay, what else needs to be covered in separation techniques? How does filtration work, guys? Filtration, remember we drew particle diagrams of this in class where we had our paper molecules. This is the filter paper particles, and we know that the paper has holes in it. I'm going to draw these holes as like gaps between these clumps of paper molecules, and anything that has particles that are small enough to fit through those holes are going to go right through the paper. If something's not going through the paper, that's because it has really big particles, or maybe those particles are in big lumps or clumps. All right, think about the sand. When we filtered out the sand and the water particles were small enough to go through these holes, but the sand particles are not. They get trapped in these holes because they're not small enough to fit through. If something is going through filter paper, it means that it's like dissolved, and it's dissolved small enough that the pieces or the particles can go right through the holes in the filter paper. Salt dissolved in water will go through the filter paper. We saw this when we did our demo, or it was actually a lab. You guys did it yourselves. You saw that the salt particles went right through, because if you tasted that salt water after it passed through the filter paper, you'll see that the salt is definitely still in there. Okay, that's filtration. Distillation. The way that we did distillation in class was we had a small beaker inside a larger beaker. We put that whole thing on a hot plate and we covered it up with some foil. This foil was shaped in a cone, right, so that when the water evaporated off or out of our mixture, remember there was like salt and dye and all kinds of grossness in here. When the water evaporated off, it hit the foil. This foil was full of ice. That ice immediately started stealing heat from our water vapor, causing the water vapor to condense back into a liquid, and it fell in here, and we were collecting nice clean water in our small beaker. The reason that we were able to separate the water out is because the water has a different boiling point. We can say it has a lower boiling point. Than the other contaminants in the water. So then the salt or the dye or any coffee grounds that might have made their way through. Spelled coffee wrong. So the distillation then separates by boiling point. That's what's going on there. Okay, I think that is just about everything on separation techniques that was commonly missed. Cool, okay, I hope that was helpful.